Welcome back. Our last video introduced some of the similarities and differences between machine learning and econometrics. And in this video, we're going to cover a fundamental concept of machine learning called the bias-variance trade-off. And this trade-off is at the heart of why we need to split the sample in the ways that I discussed at the end of the previous video. And basically, this trade-off just says that as I make my model richer and richer and able to capture more and more nonlinear patterns in the data, I'm going to have a model that increasingly is tailored to the training data and will not generalize very well to the test data. But in the end, I want a model that's going to reliably generalize beyond the training data. And so this is the trade-off that I face. And we can illustrate this mathematically by decomposing the expected mean squared error in the test set. So this is the squared expectation of the difference between y and f hat of x, which is just y hat in a typical econometrics notation. And we can decompose that as the variance of our prediction, or the squared bias of our prediction, or something called irreducible error, which is just inherent noise in the process that our model could never overcome, even if it had infinite predictive ability. And what is bias and variance? Well, bias is just how good is my model at predicting in the training set. If I have a biased model or a model with high bias, it's going to be a poor approximation of reality. And on the other hand, if I have a model with high variance, that means that the model does not generalize well to a new instance or to the test set. And another term you might hear commonly used is overfit, and that just means that the model has high variance and low bias. Low bias because in the training set, the model has a very low prediction error, but high variance because the model is tailoring itself to the idiosyncrasies of the training set. And so it's not actually getting the right signal from the training set to generalize to other instances that are representative of the problem at hand. So sometimes the word hallucination could be used for the word overfit, because the model is thinking that idiosyncratic variation in y that exists in the training set is also existing in other test set or validation set that it might come across. And then we also say that the model is underfit if it has high bias and low variance. And graphically, we can illustrate this with this diagram. This diagram comes from a textbook on statistical learning. And this is the main textbook that's most popularly used, written by Trevor Hasty and co-authors. And what this figure is depicting is, as I increase the complexity of the model on the x-axis, what's going to happen to my prediction error in the training set, which is the blue lines, or the test set, which is the red lines. And why are there a bunch of different lines? Well, because each time we decide to split our sample into training and test or validation, there's going to be some noise in how that's done and how the x's relate to the y in that particular split. And so what we care about is the dark lines, which are the averages over all the possible splits we could make, but we can still note that there's variation within each split. And that's why there's this group of lines in this graph. So the optimal complexity of the model that perfectly balances this bias-variance trade-off is where the red line is a minimum. So in this graph, it would be about at 22 degrees of freedom. And then irreducible error just means that the red lines can never go below a certain value. So here it looks like 0.3 is the absolute minimum prediction error we can ever hope to achieve in the test set. And then the blue lines are just showing that as we get overfit, we can go below that irreducible error because we're having a model that's so complex that it's assigning signal to components that are actually noise. Now, how do we measure prediction error? Well, that depends on if our y variable is continuous or not. If our y variable is continuous, we just used mean squared error to measure the fit. If y is categorical, then we need to use accuracy or some other measure. So this gets back to our video a long time ago about goodness of fit in the logit model. And in that video, I said accuracy is not a good way to measure the fit of the model. but we could do some combination of specificity and sensitivity, or precision and recall. So basically the idea is that we want to trade off. We want to come up with a metric that appropriately accounts for both type 1 and type 2 errors in the classification. So we want to severely penalize random guessing as a way to get the fit of the model to be good. And so we change our metric so that random guessing is not going to be a good rule to adopt. So that is a little bit about the bias-variance trade-off. And we haven't said anything about how we generate these predictions. But in the next video, we'll cover some basic algorithms that are popular in machine learning and that are occasionally brought over into econometrics to assist with econometric analyses. So I hope that you found this video interesting and informative, and that you'll join me for the next one.